The purpose of this lab is to use Newton's second law to compare the predicted and analyzed motions of a spring mass system that moves in a two-dimensional oscillating motion. The two main formulas I'll be using to achieve the predicted motion is by using the derived velocity and position update formula from Newton's second law. I'll be analyzing the motion of a spring mass system through the software Tracker and creating a computational model by using the software GlowScript. Additionally, we'll be using the energy principle to calculate the changes occurring in energy through the duration of the motion. The three different energy that are involved are the kinetic energy, gravitational potential energy, spring potential energy. This particular lab is important because we should be able to predict the motion of any extreme sports and other activities involving rope, so we can calculate the exact coordinates needed to do such activity in a safely manner. Now that we know the problem and why we are interested, let's move on to the tracker video. Before I begin to explain the video, a few information that needs to be given. The total system we are observing is the spring mass system and Earth. The forces interacting with our system is gravitational force and the spring force. To track the motion of the object, I set the origin of the coordinate system to start at the fixed attachment point up here. Thus, it will be negative y-axis and positive and negative x-axis that the object will be moving in. The length of the spring is 0.7 meters. From this observed model, I'll be using its initial values to create the computational model. The initial values are the position being 0.035 in the x-axis, negative 0.729 in the y-axis, and 0 in the z-axis. Velocity being 0 across all axes. Delta t is 1 over 210 seconds. Observation duration is 0.095 to 8.927 seconds. The spring constant is 6.09, and I got this by using the spring constant formula, the relaxed length being 0.0356 meters. I got the relaxed length by using the static equilibrium formula. Now that we've seen the tracker video, let's move on to the code. Firstly, I set all the given initial values given by the tracker into this code, such as the object's mass, position, velocity, timing, delta t, gravitational force, spring constant, and relaxed length. Then, on line 84, 85, 86, I use variation of Hooke's law to calculate the stretch of the spring and the direction of the spring. After that, I use the formulas of each energy from the energy principle. Kinetic energy is 1/2 times object's mass times magnitude velocity squared. Gravitational potential energy equal object's mass times gravity times position. Spring potential energy equal 1/2 times spring constant times stretch squared. And then the total energy is kinetic energy, gravitational potential energy, and spring potential energy added up. Then I set the duration to be that of the tracker video and defined the initial value so through each iteration the previous would become the initial energy values. After that, I calculate the gravitational force acting on the object by setting the y-axis to be negative object's mass times gravity, and calculate the spring force by using the spring force formula, which is negative spring constant times stretch times the unit vector. Thus, Fnet would be gravitational force plus spring force. Line 119 and 121, I updated the equation to equal to the velocity and position update formula. 124 through 139, I am using the same Hooke's law and energy principle. However, this time I am calculating the delta of each energy. Now that I've shown the code, we can see the model that was given from this code. As you see on the left image, our model is mimicking the motion of the object hanging on a spring in our tracker video, thus showing the model is working. It shows us why we chose to use this model to represent our system, because we were able to create a virtual version of our real system by using Newton's second law, Hooke's law, and energy principle formulas, and use their values to create a computational one as shown here. To further prove the point, if we look at the image on the right, it shows us the comparison of the modeled and observed motion. The blue is the modeled motion. As you see, the model is over-predicting the motion at each oscillation period. This could be due to the model ignoring the drag force, spring mass not being included in the whole system, and the late observation of the motion in the video. Now that we are done comparing the model to the observed motion, let's answer some questions from the lab. First question: The energy principle is satisfied as shown by the energy graph from our computational model. As mentioned before, our system consists of the mass of the object, spring force, and gravitational force, and no other surrounding affecting the spring. Thus, the change in energy should be a straight line, as it's shown in the graph. Question 2. If we estimated the period of oscillation using the x data instead of the y data, then we get x to be 1.574. Both x and y are very close, but the reason x is longer is because we're moving in horizontal ellipses. Thus, we have to travel further in the x direction than the y direction, this making the x oscillation period much longer than the y.